welcome you all to this digital classroom for the subject control systems. In the previous lecture, we solved few problems related to the construction of root locus. In this session, let me solve few more problems related to the construction of root locus. You can take down this question. Sketch the complete root locus of system having g of s is equal to 1 divided by s into s plus 1 into a square plus 4s plus 13. You have been given with the open loop transfer function g of s with unity feedback h of s is equal to 1. Therefore, you can say that the root locus is always symmetrical about the real axis. Let us construct the root locus by following the steps. Step 1. Step 1 is to get the general information about the number of open loop poles or zeros and the number of branches from the given g of s into h of s. Therefore, for the given open loop transfer function g of s, we have 4 poles at s is equal to 0, s is equal to minus 1, and simplifying this quadratic equation s square plus 4s plus 13 as the highest power is 2 here, you will be getting 2 more roots at s is equal to minus 2 plus 3j and at minus 2 minus 3j. Therefore, the number of poles is equal to 4 in this case, and we don't have any zeros. Hence, we can write the number of zeros z is equal to 0. We know the procedure. If p greater than z, then the number of root locus will be equal to p. Therefore, n will be equal to 4. And we know that root locus always start with an open loop pole at k is equal to 0, and it will be terminating at a open loop 0 when k reaches infinity, which means that p poles will be terminating at z zeros. In this case, as we have a number of zeros to be a 0, none of the pole will be terminating to 0. Hence, p minus z of the branches will be terminating to infinity. In this case, p is equal to 4 and z is equal to 0. Therefore, all the 4 branches will be terminating to infinity. We can write a starting point of the poles when k is equal to 0 will be at s is equal to 0, s is equal to minus 2, and s is equal to minus 2 plus 3j as well as minus 2 minus 3j. And the terminating point will be at an open loop 0 when k reaches infinity. And all these 4 poles will be terminating at s is equal to infinity, comma, infinity, comma, infinity, comma, infinity. Here it is very clear that all the 4 branches will be terminating to infinity. Then step 2. In step 2, we have to draw the pole 0 plot, and we have to identify the section of real axis for the existence of root locus. And we have to predict the minimum number of breakaway points by using the general prediction. Therefore, let us plot the location of poles and zeros in the S plane. We have a real axis and the imaginary axis, and we have a pole at s is equal to 0 and at s is equal to minus 2, and we have a complex conjugate pair at minus 2 plus 3j as well as at minus 2 minus 3j, which is the intersection point of the real and the imaginary axis. Minus 2 plus 3j. This intersection point shows the location of one complex conjugate pole, and on the other side we have another pole at this location, minus 2 minus 3j, and this gives you the location of the other pair. Once after drawing the pole 0 plot, we have to identify the section of real axis for the existence of root locus. Remember, we have to identify only on the section of real axis for the existence of root locus. Therefore, let me represent the pole which is located on the real axis. We have a pole at s is equal to 0, this is on the real axis, and another pole at s is equal to minus 2, which is also on the real axis. Now let us check for the existence of root locus on the real axis. Let me take a point here and look towards the right side and ask the question that whether you could able to see any poles on your right side. In this case, we don't have any poles and zeros. Therefore, root locus does not exist in this region. Let me take another location, some points in this region in the negative real axis between minus 2 and 0, and let me look into the right side. And we can ask the same question that whether you could able to see any odd number of poles and zeros towards your right. Yes, in this case I could able to see one pole, that is at s is equal to 0, which is an odd number pole towards the right side. Therefore, a root locus exists towards the left of an odd number of poles. Hence, in this case, root locus exists towards the left of an odd number of poles, and this existence can be traced until this region. Because once after we exceed s is equal to minus 2, if you take a location here at any point at minus 2.001 or any point, if you look into the right side, now if you ask the same question whether you could able to see any odd number of poles and zeros towards your right, now the answer will be no, as we have two number of poles, that is an even number. Therefore, root locus does not exist towards the left of an even number of poles and zeros. This region will be NRL, and the root locus exists only between minus 2 and 0. Hence, we can write here as root locus exists between minus 2 and 0. Let us mark the region of root locus on the real axis, and you can mark it as RL, that is a region of root locus. Remember, we have to identify only in the section of the real axis for the existence of the root locus. We should not take the complex pole into consideration when we check for existence of the root locus on the real axis. And in the meantime, let us predict the minimum number of breakaway points using general prediction method. We know the general prediction method that if you have any two adjacently placed poles, in this case I have two adjacently placed poles, and these two poles should be in the region of root locus. Yes, of course, these two poles are in the region of root locus at s is equal to 0 and minus 2. Therefore, there exists minimum one breakaway point. Making use of general prediction, now we have predicted that there exists minimum one breakaway point between minus 2 and 0, and let us justify this in the coming steps. Moving on to the step 3. Step 3 is to calculate the angle of asymptotes, and step 4 is to determine centroid. Both the steps comes hand in hand, and we can plot it immediately on the S-plane. Let us calculate the angle of asymptotes. The formula to calculate the angle of asymptotes is given by theta equal to 2q plus 1 into 180 degree divided by p minus z, where q ranges from 0, 1 and so on up to p minus z minus 1. In this case, the number of poles is 4 and the number of zeros is 0 minus 1. So 4 minus 1, it's 3. Therefore, the range of Q is from 0, 1, 2 and 3. That is what specified here. For the first case, let me substitute for Q as 0. Therefore, theta will be equal to 180 degree divided by P minus Z, where P is 4 and Z is 0. Therefore, 180 degree divided by 4, it will be equal to 45 degree. Similarly, if you substitute for Q as 1, 2 plus 1 into 180 degree divided by 4, that is 3 times of 180 degree divided by 4. Therefore, theta 2 will be equal to 135 degree. And for the third case, substituting for Q equals 2, we get 5 times of 180 degree divided by 4. Therefore, theta 3 will be equal to 225 degree. And finally, substituting for Q equal to 3, 3 into 2 plus 1, that is 7 times of 180 degree divided by 4, that is theta 4 will be equal to 315 degree. Let us calculate the centroid making use of the formula summation of real part of poles minus summation of real part of zeros divided by P minus Z. Therefore, we have a pole at S is equal to 0, S is equal to minus 2, and a complex conjugate pole at minus 2 plus 3j, as well as at minus 2 minus 3j. As it is only for real part, I have taken only the real part from this complex conjugate pole. That is minus 2 minus 2. This is from the real part of the complex conjugate pole. Minus of summation of real part of zeros. We don't have any zeros, hence this case will be taken as 0. The whole divided by P is 4 here and Z will be equal to 0. Therefore, further simplification, centroid will be equal to minus 1.5. Now let us plot the centroid on the S-plane. The S-plane is as shown here, and the location of the pole is at minus 2, and we have the location of pole at minus 2 plus 3j as well as at minus 2 minus 3j, and we have a pole at an origin at S is equal to 0, and the yellow color line highlights the region of the root locus. And now we have the location of the centroid exactly at minus 1.5. We have marked for the centroid now in the S-plane. I told you that step 3 and 4 comes hand in hand. So once after marking for the centroid, we have to make use of the protractor, and with the centroid as the reference, we have to mark the angle of asymptotes exactly at 45 degree, 135 degree, 225 degree as well as 315 degree. Let me take the protractor, and with centroid minus 1 as the reference, exactly have fixed the origin of the protractor exactly at minus 1.5. Now let us mark for 45 degree. It's exactly 45 degree here. Let me mark for 45 degree the first angle of asymptote, and then mark here exactly. And then we have an angle of 135 degree exactly here in this region, 135 degree. And let me mark for the second angle of asymptote. This is the exact location. And let me reverse the protractor and mark for the rest of the two angle of asymptotes, having again the centroid as the reference. Angle is exactly 180 degree. So we have to mark for the third asymptote theta 3 at 225 degree. So this is 190, 200, 210, 220, 225 degree, exactly here in this region. Let me mark for it. And the fourth asymptotes will be exactly at 315 degree. This is exactly 270 degree. Therefore 280, 290, 300, and this will be 310, and another 5 more, that is 315 degree. It comes exactly in this region. Now let me take the ruler. First let me mark for 45 degree, that is the first angle of asymptotes having centroid as the center of the asymptotes. So centroid act as the center of this asymptote, and let us join the lines with respect to theta 1 at 45 degree. That is the angle of first asymptote. Marked in dotted lines. I have joined the lines from the centroid towards the first angle of asymptote exactly at 45 degree. Now again with centroid at center, let me mark for the second angle of asymptote exactly at 135 degree. With centroid being the center of the asymptote, let me join the line of the second angle of asymptote, which is at exactly at 135 degree. Similarly, let me mark for 225 degree as well as 315 degree. Extending the line from the center of the asymptote as minus 1.5, which is the centroid. Let me mark for the final asymptote, which is at 315 degree exactly. This is the angle of asymptote exactly at 315 degree theta 4, which has been extended from the center of the asymptote exactly at sigma is equal to minus 1.5. Therefore, we have the final asymptote theta 1 at 45 degree, then theta 4 at 315 degree, then with theta 2 at 135 degree, and we have an asymptote exactly at 225 degree. And the angle of the first asymptote from the real axis is 45 degree, and the second asymptote is 135 degree, and the third asymptote is 225 degree, and the fourth asymptote is 315 degree. Making use of step number 3 and 4, we have plotted the angle of asymptotes as well as the centroid. Moving on to the next step. The next step is to calculate the breakaway point. We know the procedure to calculate the breakaway point. The first step in calculating the breakaway point is to write a characteristic equation. Let me write the characteristic equation 1 plus g of s into h of s equal to 0. Given g of s is equal to k divided by s into s plus 1 into s square plus 4s plus 13. Let us substitute for g of s in the characteristic equation. For the simplification, I get the expression as s to the power 4 plus 6s cube plus 21s square plus 26s plus k equal to 0. And we know the procedure. We have to represent in terms of k, taking the rest of the s term towards the right side. I get the expression for k as k equal to minus s to the power 4 minus 6s cube minus 21s square minus 26s. Now we have to differentiate k with respect to s, that is dk by ds, and we have to equate it to 0. Therefore, I have equated the expression equal to 0 minus 14s cube minus 18s square minus 42s minus 26 equal to 0. As we have the highest power of s as 3, simplifying this expression gives you 3 roots. Once after getting the three rods, we have to check for the validity of the breakaway point. Solving this above expression, we get three rods, one at S is equal to minus 0.8929 and the other two on the complex conjugate pole at minus 1.8 plus or minus 2j. Now let us check for validity. We have marked the centroid, the angle of asymptotes, and the region of root locus. And now let us check for validity. S is equal to minus 0.8929 is exactly located between two adjacently placed poles, and these two adjacently placed poles is also in the region of root locus. Therefore, minus 0.895 becomes a valid breakaway point. As already predicted that if we have two adjacently placed poles, and if these two adjacently placed poles are in the region of root locus, yes, minus 2 and 0 or two adjacently placed poles and they are in the region of root locus, then there exists minimum one breakaway point. This is what we predicted before, and we never knew the location where it is located. And exactly at this location, multiple poles occurs. That is, when k equal to 0, we have a pole at minus 2 and at 0. And when k increases, there will be a movement of these poles in this direction and for 0 pole towards this direction. And a particular value of k, these two poles will intersect with each other and they meet at a single point. And this is the point at which breakaway occurs. And this will be the maximum value of k on the real axis. And once after k exceeds beyond this value, it moves from real axis towards the complex plane. And for the other two roots, minus 1.8 plus or minus 2j, we have to calculate for the angle and the magnitude condition, and we have to check whether this point lies on the root locus or not. We check for that condition, this becomes invalid. Therefore, S is equal to minus 0.8929 is a valid breakaway point. The next step is to calculate for intersection of the root locus on the imaginary axis, that is step 6. Once after identifying the breakaway point, the root locus tries to break away and it tries to move away from the real axis into the complex plane, and it will be following the path which has been guided by the asymptotes. In this case, we have two asymptotes exactly at 45 degree and 315 degree. Therefore, the root locus will be guided by these asymptotes in this direction, and at exactly at one point, these two root locus will be intersecting on the imaginary axis. At a particular value of k, we get two roots on the imaginary axis, and we can represent it as k margin, which is making the system to be as marginally stable condition. Therefore, we have to find the location of that root which is getting intersected on the imaginary axis. That is what we are going to find for in step number 6. Let us find the exact root which is going to intersect on the imaginary axis, making use of step 6. Step 6, intersection with imaginary axis. We know the procedure. The first step is to write the characteristic equation. We have already written the characteristic equation in step 5. That is s power 4 plus 6s cube plus 21s squared plus 26s plus k equal to 0. The next step is to generate the Routh array. We have generated the Routh array and we can fill up the first two rows here. First write the coefficients, then fill up the first two rows, taking the coefficients of s power 4 as 1, then s cube as 6, beside that, then s square coefficient 21, s coefficient 26, then we have a constant k, and fill up the rest as 0. To fill up the third row first element, we know the procedure. 6 into 21 minus 1 into 26 divided by 6. I can write it here as 16.667. Similarly, to find the third row second element, we can form the pattern 6 into k minus 1 into 0 divided by 6. 6 in the numerator and denominator will get cancelled out, therefore I get k. The third element will be equal to 0. Moving on to the next row, that is s to the power 1 row, the first element can be written as 16.667 into 26 minus 6 into k divided by 16.667. Therefore, I will get 433.33 minus 6k divided by 16.667. The second element will be equal to 0. And for the last row first element, I can make use of the previous two rows and make use of the pattern. The first element of s to the power 1 multiplied by k minus 16.667 into 0 divided again by the same element. As it is in the numerator and denominator, it will get cancelled out. Therefore, I get k. And as I told you before, the constant term will be shifted back again to the same coefficient of s to the power 0 provided this term is 0. Now to find k margin, we know the procedure. We have to equate the s to the power for first row, first element equal to 0, which means that we have to make the s to the power 1 row as a complete 0 row. If it is a complete 0 row, it results in a special case 2 of the Routh criterion, for which we used to take the previous s to the power 2 row as an auxiliary polynomial, and then if we simplify the roots of the auxiliary polynomial, we get the location of the roots on the imaginary axis, which is making the system to be as marginally stable. Therefore, let us equate the first element of s to the power 1 to 0 and calculate for k margin. From s to the power 1 row, 433.33 minus 6k equal to 0. Further simplifying, I get k margin equal to plus 72.220, which means that if I substitute for k as 72.220 here, this term will become 0 and it becomes a complete 0 row. So let us take the auxiliary polynomial as 16.667 a square plus k, which is equal to 0. Simplifying this auxiliary polynomial, we will be getting two roots exactly at plus or minus j 2.081, and this is the exact location at which the root locus is going to intersect on the imaginary axis for k margin at 72.22, which is making the system to be as marginally stable. Let us locate this root on the imaginary axis. We have the location of poles here, the angle of asymptotes. Students, for the examination, it is not necessary to plot it again and again. Once after following all the steps in one flit, we can plot the root locus as a complete sketch of the root locus. I have done this only to make you to understand the step-by-step procedure. We have marked with the centroid and the location of breakaway point exactly. And now let us mark for the intersection of the root locus on the imaginary axis, which is exactly at plus j 2.081 as well as at minus j 2.081. And as I told you before, when k increases, there will be a movement of these poles in these regions and it breaks away and the root locus starts moving from the real axis into the complex plane, and it will be following the path of the asymptotes, the direction of the asymptotes. The asymptotes are the one which is going to guide this root locus, and it will be guided in this direction, and it will be exactly intersecting on the imaginary axis at these two locations exactly when K margin equals to 72.22. And once after K margin increases beyond 72.22, the root locus moves into the right half of the S-plane, and this completely makes the system to be as unstable for K margin greater than 72.22, and it is clearly seen here, and these two branches will be reaching infinity. Remember, the root locus will be taking its direction by looking into the angle of the asymptotes. There is no possibility for this root locus to get diverted in this direction, as we don't have an asymptote which is guiding towards 135° as well as 225° for this particular breakaway point. These are the few important points which has to be taken into consideration, because following the steps is a different aspect which we follow making use of the procedure, and we get a valid points and the locations on the S-plane. But predicting the path of the root locus and its direction is completely based upon our prediction. So you have to concentrate on this issue. Almost 70% of the plot is done, as we have done with two of the root locus branches. The left out step is only with respect to the calculation of angle of departure for the complex conjugate pole. And now we have to calculate the exact angle of departure at which these poles try to move from its complex plane. At exactly what angle does it depart? And once after calculating this angle of departure, it gives you the complete sketch. So let us move on to the next step, calculating the angle of departure. Step number 7 is to calculate the angle of departure of a branch of root locus from a pole is given by, that is complex conjugate pole, phi d is equal to 180° minus phi, where phi is given by summation phi p minus summation phi z, where summation phi p is the contribution by the angles made by remaining open loop poles at pole at which phi d is to be calculated. Also, summation phi z is the contribution by the angles made by the open loop zeros at the pole at which phi d is to be calculated. So let us solve for the calculation of angle of departure. Again, I have located the poles and zeros. Now our point of interest is to calculate the angle of departure for the complex conjugate pole at -2 plus 3j. Therefore, we know the procedure. We have to calculate the angle of contribution for the rest of all the poles and zeros towards the point of interest. Our point of interest is to calculate the angle of departure for this pole. Therefore, we have to calculate the angle of contribution towards the pole at s is equal to 0, then the pole at s is equal to -2, as well as the complex conjugate pair, which is located exactly at -2 minus 3j towards the point of interest. We know the formula phi d equal to 180° minus phi, and the first step is to join all the line from the rest of all other poles and zeros towards the point of interest. Now we are going to calculate the angle of departure for -2 plus 3j. Therefore, let us join all the lines from the rest of all the poles. From 0, it is extended. From -2, it is extended towards the point of interest. And as well as from -2 minus 3j, that is the other pair, again we have extended here. And we have to calculate its angle of contribution towards the complex conjugate pole, which you are going to calculate for angle of departure. These angles we have to calculate. We know phi is given by summation phi p minus summation phi z. For angle of departure, let us calculate for phi p1, that is angle of contribution for a pole located at s is equal to 0. Let it be phi p1, where phi p1 is given by, to calculate the angle phi p1, I can take this complete angle as 180 degree minus this angle to be as x. So I can write it as 180 degree minus x, where x is given by, you can take this as a right angle triangle, where x is given by tan inverse of, this gives you the opposite side, and this will be the adjacent side. The projection on the imaginary axis, this is 3 here, and on the real axis, this is 2 here. Therefore, let me take this right angle triangle and write it as tan inverse of 3 by 2. That is tan inverse of b by a. Further substitution and simplification, phi p1 will be equal to 123.69 degree. This angle will be 123.69 degree. Let us calculate for phi p2. This is 0 degree and this angle is exactly 90 degree. Therefore, contribution of the pole at -2 -3j towards the point of interest is 90 degree. I can write phi p2 as 90 degree, as well as phi p3, again for the angle of contribution for a pole located at -2, this angle will be exactly 90 degree. So phi p2 and phi p3 will be equal to 90 degree. Once after finding for phi p1, phi p2 and phi p3, we know that phi is equal to summation of phi p, that is sum of all the angle of pole contribution towards the point of interest. As we don't have a 0 here in this example, phi z will be equal to 0. Therefore, I can sum up all the angle of contributions, 123 degree plus 90 degree plus 90 degree, that is phi p, 123.69 degree plus 90 degree plus 90 degree. I will be getting 303.69 degree, and summation phi z will be equal to 0. This is plus. Once after finding for summation phi p, now we have to substitute for phi. Phi will be equal to 303.69 degree. Then phi can be substituted in this expression. That gives you the angle of departure for the pole at -2 plus 3j. Therefore, phi d will be equal to 180 degree minus phi. Substitute for phi here. Therefore, the angle of departure is given by minus 123.69 degree at -2 plus 3j. As we know that the root locus is symmetrical with respect to the real axis, the angle of departure for the pole located at -2 minus 3j will be plus 123.69 degree. It's not necessary for you to calculate for the other end. You can write it directly. To calculate the contribution of these angles, either you can make use of this formula or you can make use of the protractor measuring these angles and writing it directly. I will show you how to calculate with the protractor. To calculate for the angle of contribution, we can make use of the protractor. Exactly, now let us calculate the angle of contribution for the pole at s is equal to 0. So if you measure this angle, the dotted line which has been extended towards the point of interest, this will be exactly at 123 degree. This shows you the exact angle which has been measured here, making use of the formula. Both are one and the same. Now this angle is equal to 123.69 degree. We can measure with the protractor directly and we can substitute. This is another method of calculation. You can follow this procedure also. Similarly, the angle of contribution for the rest of the pole, 1 at s is equal to -2. It is very clear that it will be exactly 90 degree. Also for this pole, again this will be also equal to 90 degree. So you can follow this procedure, calculating the contribution of rest of the angles towards the point of interest, making use of the protractor also. Now let us mark for the angle of departure at minus 123.69 degree for the complex conjugate pole at -2 plus 3j. The angle of departure is given by minus 123.69 degree. If you take the clockwise direction, this angle will be 90, 180, 270 and so on. As the angle is negative, we have to take the angle in the clockwise direction. Having -2 plus 3j as the reference. I have fixed the center of the protractor exactly in this location. And let us plot for -123 degree. If you move in the clockwise direction, this angle will be -90 degree, -100 degree, 110 degree, 120 degree, 121, 122, and exactly this angle will be 123 degree. Let us mark this angle. This gives you the angle of departure. And let us represent this angle extending in dotted lines. This gives you the angle of departure. Similarly, for the other pole, which is located at -2, -3j, let us fix the center of the protractor exactly in this location. And we have to mark for the angle, which is given by plus 123.69 degree. As it is positive, we have to take clockwise direction. This angle will be exactly 90 degree. So let us mark for plus 123 degree. 114, 115, and we have reached 120. And exactly 123.6. Let me mark here. This comes somewhere here. Yes, this is the exact angle. And let me mark for this angle. And let us extend this line representing the angle of departure for the other complex conjugate pole. Now we have marked for both the angles. And this angle exactly will be equal to minus 123.69 degree, and this angle will be exactly equal to plus 123.69 degree. Now we know that exactly at an angle of minus 123.69 degree, the poles will try to depart with respect to the increase in value of k, and the asymptotes as it is guided at an angle of 135 degree as well as 225 degree, these branches will be guided by these asymptotes. Similarly, on the other side, the other pair of complex conjugate pole will be departing at an angle of plus 123.69 degree, and it will be departed following the direction of the asymptote at 225 degree, and it tries to reach infinity when k value increases and reaches infinity. And now let us plot the angle of departure and the movement of these complex conjugate poles on the S-plane. Now let us look into the complete root locus plot, step 8. This gives you the complete plot of the root locus, the location of the poles and the complex conjugate poles, as well as the angle of asymptotes and the region of root locus, and the location of the centroid and the breakaway point, and the intersection of the roots on the imaginary axis, as well as the angle of departure phi d at 123.69 degree for the complex conjugate pole, and the movement of these poles has been shown here, which has been guided by the asymptote at 135 degree and 225 degree, which is trying to reach infinity. And this shows the final sketch with the direction of root movements as k increases from 0 to infinity, and it is shown very clearly here. We can see the movement of the branches for the complex conjugate pole, which is trying to reach infinity here. P3, P4 represent the branch number, and we could able to see the movement of the pole on the real axis at s is equal to 2 as well as at s is equal to 0. This shows the movement of these poles when k increases. Step number 9 gives you the range of k. When k ranges between 0 and 72.22, the system is absolutely stable. And exactly when k is equal to 72.22, that is k margin, we could able to find a root which is intersecting on the imaginary axis, which is making the system to be as marginally stable. And when k exceeds beyond 72.22, we could able to see the movement of these poles, which is reach the right half of the S-plane. Therefore, the system becomes unstable. This is how we have to write for step number 9, speaking about the stability. And it is very clear and evident that all the 4 root locus branches are trying to terminate at infinity, which has been guided by 2 asymptotes, 45 degree and 315 degree for the pole at -2 and 0, as well as for the complex conjugate pole, 135 degree asymptote and 225 degree asymptote is trying to guide it towards infinity. Finally, let us compare the output with the MATLAB. Given g of s equal to 1 divided by s into s plus 1 into s square plus 4s plus 13. For the simplification, g of s will be equal to 1 divided by s power 4 plus 6 s cube plus 21 s square plus 26 s. And we know that as we don't have any zero, the numerator polynomial, we have only one constant, we can write it as 1. And the denominator polynomial, the coefficient of s power 4 is 1, s cube is 6, and s square coefficient is 21, and s coefficient is 26, and the constant term here is 0. Therefore, making use of the command or locus of num, comma, den, this gives you the complete plot of the root locus. Let me click on this icon MATLAB. In the command window, let me write the numerator polynomial 1 in this example, followed by the denominator polynomial. We have s power 4. So the coefficient of s power 4 is 1. 6s cube, then 21s square plus 26s, and we have a constant 0. Therefore, R locus of num, comma 10 gives you the plot. Gives you the plot of the root locus. The complete sketch of root locus can be visualized here. We could able to see the complete sketch of this root locus. We have the location of pole at s is equal to 0 and another pole at s is equal to -2, and we have a complex conjugate pair at -2 plus 3g as well as at -2 minus 3g, and this region of root is very evident here, and there exists minimum one breakaway point. Therefore, when k increases, we could able to see the movement of these pole in the, and for s is equal to 0 towards this direction, and they intersect together at one single point at which multiple pole occurs, and we call it as a breakaway point, and it is breaking away and it is intersecting on the imaginary axis exactly at k margin, at which the system is becoming marginally stable, and when k keep on increasing, it is moving on to the right of the s-plane, then it reaches infinity. The system becomes unstable when k exceeds k margin, and when it is exactly at k margin, the system becomes marginally stable. Whereas here on the other side, we could able to see the angle of departure of this complex conjugate pole exactly at minus 123.6 degree, and this pole is trying to move in this direction of the angle of asymptote at 135 degree as well as 225 degree departing, and these two branches also try to reach infinity. Let us compare with our output. In comparison with the output which we have got from MATLAB, we can compare with our results. It's exactly one and the same, and we could able to see exactly the movement of these branches which is trying to reach infinity. So we have done with this problem. In the next lecture, let us solve few more example problems related to root locus. Thank you.